and weak, right? Okay, so let's begin the class. You are going to have an exam on Wednesday. We will talk about the exam after we are done with the shock waves and expansion waves. Hopefully we can finish the shock waves and expansion waves today, and we will solve 2 examples. Your homework is already posted, but your homework is not due until October 18th. Because your homework includes whatever that we haven't covered so far in chapter 2.
So that's homework 3?
That's homework 3, yes, yeah. It has like 2 questions on the shock waves, but the rest of them are questions on the Fano flow and the Rayleigh flow, which we will discuss later after the exam. So let's begin with the waves in supersonic flows. We will solve a couple of 2 or 3 examples from these, just to make sure you are prepared for the exam, because you will have a question from shock waves in your exam, and then we will talk about the exam. Okay, so let's begin. Waves in a supersonic flow. If you recall, we talked about this, that since we are in a supersonic flows, your object or your flow doesn't have time to adjust for the presence of an obstacle in front of it, right? So that adjustment will be abrupt, right? So we will see a huge change in pressure, velocity, all of the flow parameters in a very short amount of time. It almost looks like there's a discontinuity in the flow. So like, let's say you have a supersonic flow, Mach higher than 1, and then you have an object in front of it. Right? As soon as your wave sees the object, you are going to be hit, your flow is going to be hit with a discontinuity. What does this mean? That the flow properties before the shock wave, upstream the shock wave, is going to be different, very different from the flow properties downstream the shock waves. Mach number, velocity, pressure, all of those things will change significantly, right? There are different types of waves in supersonic flow. We are going to start the discussion by a special case of these waves, which is called a normal shock wave. And by normal, we mean it is normal to the flow. So if your streamlines are moving in this direction, a normal shock wave is going to be normal to the streamlines, right? Before and after, this is the strongest shock waves you will see. And what does it mean? What does a strong shock wave mean? It essentially means that you're going to see the biggest changes before and after the shock wave, upstream and downstream the shock wave. You will definitely have a supersonic flow approaching this shock wave, and after a normal shock wave, you will definitely have a subsonic flow. Okay? What does it mean for the pressure? So very high velocity, V1 very high. I don't want to. Very high. And V2 much lower. What does this mean for pressure specifically?
High pressure on the left half, lower pressure on the right half.
So Nicholas is saying that P1 is going to be larger than P2, right? Do you have any other opinions? So Drew saying that it will be the other way. Can any of you elaborate on your opinion? Or if there's anyone else who wants to jump in?
So
I was thinking since after the shock wave, the Mach number is gonna be, the speed is gonna be slower than max speed, then the pressure needs to be higher on the, after the shock wave, so it's because it's not moving so fast.
Yeah, go ahead.
I think it's going to be P2 is higher than P1. Because I was thinking about it in terms of Bernoulli's principle. I'm not sure if that applies here, but the lower the velocity, the higher the pressure.
Bernoulli's principle doesn't apply here, but the lower velocity, higher pressure, that principle applies here. So you are correct. And I mean, whoever had the same opinion. I'm sorry, Nicholas. We were wrong here. So yeah, so this essentially means that your pressure is going to increase. All of the other properties will actually change as well, and we will talk about all of the other properties. So to understand the changes before and after the shockwave, downstream and upstream shockwave, let's actually create a control volume. Let's write the conservation equation of the fluid equations for this control volume. So this is a one-dimensional flow, right? So flow is coming in from this wall 1, that's this surface 1, and is going out from surface 2. What is the conservation of mass for this flow? Area of this surface doesn't change. M1 is equals to M2. Rho AV, rho A1 V1 is equals to rho 2 A2 V2. In this specific case, area doesn't change, so rho 1 U1, because it's a one-dimensional velocity, is going to be equal to rho 2 U2. This is going to be your conservation of mass. Conservation of momentum, or the momentum equation. The momentum equation is going to have two sides. One side, I'm not going to go into the details of it, but the momentum at surface 2 minus momentum at surface 1 of the control volume, the inlet of the control volume, is going to be equals to the changes in pressure force, which is the only force that is present here. Or we can actually move the pressure to one side. Move all of the properties of outlet to one side, all of the properties of the inlet to the other side. And this tells us, this stands for fluid impulse, but we will talk about it later. This tells us the impulse is going to be constant over a normal shock wave. We can actually use the simplifications and the other forms of these equations that we have seen in previous lectures and replace your velocity with a Mach number, then come up with this very nice looking equation. So this is going to be your momentum equation. Conservation of mass, momentum equation, and eventually we need the energy equation. Energy equation, the total energy of the inlet is going to be your enthalpy, a static enthalpy, plus, let's call this the dynamic enthalpy, but we don't really have that term. Kinetic energy, right? Equals to Cp T2 plus U2 squared divided by 2. So these are the governing equations. We have seen these equations before, at least maybe in a different form, but these are the same principles: conservation of mass, momentum equation, and also the energy equation. And we want to use these equations to find the relationship between m dot and m2. Find the relationship between, this is m2, so a Mach number after the shock wave and Mach number before the shock wave, the upstream Mach number and the downstream Mach number. I'm not going to go through the derivations. I'm just going to give you the final equation which we are not going to use actually, even this final equation. So Mach number dynasty in the shock wave is going to be equal to 2 plus gamma minus 1 and 1 squared divided by 2 gamma and 1 squared minus gamma minus 1. So for a normal shock wave, you will probably be given an upstream Mach number. This is like your flight velocity, right? And you will be asked the flow over a wing. Yes?
What are you plugging in to get that? Because I'm 100% lost.
Can you repeat the question?
What are you plugging in to get that equation? Because I'm 100% lost.
So to get from this location, from these three equations, to this equation, this is a long wave. And I don't want to go over the derivation. Okay? But if you want to know the derivation, we can talk about it after the class. Okay? Jacob, right? Joseph.
Yes, sir.
Joseph. But then again, you really don't need these equations. So just write them down, know they exist, and I'll tell you how to solve the problems involving the shock waves. It's much easier than using all of these equations, okay? Okay. And we actually can find the relationship between the densities and let me just write down the equation for you. And also pressures and also temperature, which based on the ideal gas law is just the pressure ratio multiplied by the density ratio. But as you can see, these are very long equations, right? So what we have done is that we have tabulated the results of these equations. You don't really need to use the equations to solve this problem. You can just go use the tables. Where can we find the tables? Everywhere, essentially. But if you have the book, you can come to the appendices, and this is the appendix C, the normal shock table. So what they have done for you, and this is a very, you see they have all of the equations here listed here that we just mentioned, except for these, the total pressure ratios for a Mach number. For an incoming Mach number, let's say your Mach number is whatever, 1.98. The downstream Mach number, this is a Mach number after the shock wave, is given to you. The ratio, temperature ratio is also given to you. The pressure ratio is also given, and all of the other properties, right? So, if you want to use the equations to solve the problem, you are welcome to do so, but you have the tables available, right? I haven't seen anyone who uses the equations, honestly. Any questions? Did this help with the confusion, Joseph? You don't need the equations at all.
I mean, it didn't help me understand the equations, but you said I don't need them, so I'll take them.
Let's actually do this to help you with the understanding. I actually have this derivation in my notes, right? That's a bonus point. If you start from the conservation equations, and get to the M2 equals to a function of M1 equation, this equation. So start from these three equations, get to this. Okay. Essentially, what you are, the only thing you really need to do is to replace these pressures, right? You already have a relationship between M1 and M2. Just have to find the replacement for the pressure ratios, right? So you already have a couple of equations for the isentropic relations and all of those things, right? It is not.
Just a second, so I can write down the next question.
So, normal shock waves. Why are they there? What is the physical reason for their presence, for their formation?
Because the body traveling in supersonic is blunt and it allows for normal shockwaves rather than oblique ones.
No, I'm not specifically asking about normal shock waves. I'm asking about shock waves in general.
Like the overlapping of sound waves.
That's the shock waves, right? But why do we have shock waves?
Because the air in front of the ring can't, like we were talking about it, it doesn't have time to go ahead and start forming over the ring. It's basically
Exactly. And so streamlines don't have the time, don't see the objects in advance to bend, essentially, right? That's a very simple explanation. That's why we have them, right? How do we analyze it? Why do we have a normal shock wave? Actually, let's actually hear Igor's response. Why do we have a normal shock wave better compared to other types of shock waves that we will talk about?
Say when a blunt body passes through supersonic flow, that big cross-section area causes it to be a 0-degree wave.
Okay, exactly. So essentially, as I said, this normal shock wave is a special case of shock waves, right? Why do we have the formation of a normal shock wave? Let's say you have a blunt body, right, that is moving through a space. If you magnify this part of it, it will look like just a wall in front of your flow, right? And this wall is the ultimate obstacle in front of the flow, right? Because of this very huge obstacle in front of the flow, the shock wave is going to be detached from the body. So the adjustment has to happen away from the body. It cannot happen on the body. So we cannot have shock wave formation on the body itself, right? It has to happen in front. And it has to be a very abrupt change, very strong change, right? Because it is a very huge obstacle in front of the flow. It is not like an airfoil, right? An airfoil just bends the streamlines. But like plane surface, whatever, a plate in front of the body is going to cause a stagnation point, and then it will completely bend the flow 90 degrees, right? That's what's going to happen. So we are going to need a strong shock wave. And a normal shock wave is the strongest type of shock wave. Okay.
You always have at least like one. If you can zoom in on an airfoil.
No, not necessarily. Not necessarily. It has to be a very blunt body, right? Yeah, no, that doesn't happen necessarily. Okay, but what is the general type of these shock waves? This general type is called an oblique shock wave. Let's say we have this type of geometry, or a slender body, right? Doesn't matter exactly. The streamlines are coming this way, and then they will see this object. We are moving in a supersonic flow, so we don't have the time to adjust before this. So the streamlines cannot bend, right? What is going to happen is that they have to bend just as they reach the body, right? Or even sometimes as they have already passed the body. Let's actually And these streamlines are going to get closer to each other. All right, this is what's going to happen. So the shock waves that are forming here in this type of bodies are going to compress the flow. The streamlines are going to get closer to each other. Normal shock waves are a special type of these shock waves specifically. The oblique shock waves are going to compress the flow. As you can see, the direction of the flow in this type of shock wave is changing. Okay, so if you want to have the equations in the direction, in the x direction, you are going to have rho 1 u1 also rho 2 u2, right? 1, 2, before and after the shock. And again, in the x direction, we are still going to have the momentum equation. And also, or let's call this CPT. Okay. If you recall, this momentum equation is an interpretation. If you remember this, we just discussed this, right? Is an interpretation of the Newton's second law, which means that the direction is important here, right? It is a vector form of equation, meaning that we have actually this equation applies to every direction. Since your flow is two-dimensional, we are going to have to write the momentum equation in the other direction as well. So you have u which stands for the flow in the x direction, velocity in the x direction, and you also have, let's call this w, right? Flow in the y direction. See, it is moving, the velocity vector is in this direction. Projection of it in the x direction is going to be u. Projection of it in the z direction is going to be w. Okay? So let's write the momentum equation for this. Rho 2 w2 minus rho 1 w1. Again, p1, p2, and this is multiplied by the area in that direction. But you don't need to write this part because the pressure doesn't change in that direction. That's the first assumption we are making. So this is equals to 0, which eventually means that the velocity is going to be equal to, velocity is not going to change. Right? This direction of velocity, this part of the velocity vector is not going to change. So the only part of the velocity vector that is changing is the projection of velocity or the component of velocity in the x direction. Okay? Yes.
So does that mean density stays the same in the y direction?
No, we are missing the u part of I shouldn't have used this momentum equation. Just accept that velocity dimension. That was my mistake, I'm sorry.
So if the air is coming in with no vertical component, how can it have a vertical component after the shock wave?
That's okay. We are actually writing this is going to be your normal component, and let me magnify this part. This is your shock wave, right? This is going to be your x direction, this is going to be your w direction. Okay? Does it make sense?
Okay.
So your u is always normal to the shock wave.
So we're just changing our frame of reference?
Yes. Okay. So for this equation is going to be the W part of this V1 is going to be equal for both sides. So this will cancel out. And we are going to end up with CPT1 plus U1 squared divided by 2. CPT2. CPT2 plus U2 squared divided by 2. This is an equation we had in the normal Shockwave calculations. This is an equation we had in the normal Shockwave calculations. This is also an equation we had in the normal Shockwave calculation. So the equations in the direction that is normal to the Shockwave are going to be exactly the same. So same equations. For the direction that is normal to the Shockwave. What does it mean? It means that as long as we are finding the velocity or the Mach number, the normal component of the velocity or the Mach number, we can actually use the normal Shockwave tables. Right? That's it. So the only thing we really need to do here is to find the normal components of the Shockwave. So normal component of Shockwave in the upstream direction is going to be equals to, you have a question? Your Mach number of the upstream sine of beta, right? This beta is going to be this angle. This is going to be theta. That's your this is a concave, right? Concave angle. It's a geometrical angle. So in the slender object, this is going to be your angle beta. As long as you're finding the normal component of it, you should be fine. You should be able to go back to the normal shock tables, and then you will find the normal component of downstream Mach wave.
So beta is the angle between the airfoil and the chord line, and then beta is the angle from the chord line to the shock wave? Not the airfoil to the shock wave?
Yes. This is the deflection angle. How much this is called the deflection angle. How much your stream is going to be deflected. Okay, and let's continue. So you find the M2 using the tables, and then you'll find the M2n using the tables. Then you find M2 by this equation, beta minus theta. Then all of the other properties you can find from the tables. Okay, but this deflection angle is something that we need to determine from there is a relationship called the Theta Beta M relationship. Right? We are not going to talk about the relationship, but we are going to see the plot that connects the two relations. Let me bring it up. very, very huge figure, right? So you are going to have the deflection angle delta or theta, for it doesn't really matter which one you choose, and you're going to have the shock move angle beta, and these lines are the Mach number lines. As you can see, so this is what's going to happen when you're dealing with a normal an oblique shock wave. You will be given one of these angles, and I mean not in quotation, they're literal angles, and the Mach number, and then you come to this table, you determine the other angle, right? Based on that other angle, you can do the calculations to find the normal components. Then you go to the normal shock tables, you read the values, you find the Mach number after the oblique shock waves. Okay, but as you can see, for every deflection angle, we are going to have two betas. For every deflection angle and Mach number, we are going to have two betas. So this is how the plot actually looks like. Actually, so beta, theta, this is going to look like this. Let's say this is Mach, whatever value of Mach, this is Mach constant. These are constant Mach lines, right? So for each value of theta and a constant Mach number, you're going to have two betas. Why is this happening? Or what does this mean?
Isn't it just because it has a shockwave on both sides of whatever is creating the shockwave? It's going to.
What do you mean by both sides? You mean like at the leading edge and the trailing edge? Is this what you mean?
No. At the top and the bottom of the wing.
That top and the bottom of the wing. Not necessarily. No, it is. It may actually relate to that, but not necessarily. I will say yes.
Two different betas can produce the same theta.
Yeah, but what does it mean?
Well, two different angles on your airfoil or whatever is deflecting the stream can produce the same deflection angle. So that means that there's similar properties within whatever two angle relationships.
Okay. Anyone else? Do you guys want to jump in? I mean, you're not wrong. You just essentially said for each deflection angles we have two beta, right? Which is, it was an explanation of the phenomena.
Is one imaginary?
There is no imaginary, no. Let's see the compressible fluid flow guy, what has to say. Igor.
I haven't seen this before, but is it like one is a sine and one is a cosine relationship, or?
Okay, no.
Okay.
Oh, you haven't seen it yet?
No.
Okay. So this actually means that we are going to have two types of shock waves, oblique shock waves, for each theta. One is called a weak shock. One is called a strong shock. And the angle is going to be different. So your shock is going to be a little closer to a normal shock wave, right? But why, or what is the situation, or how can we determine whether we are going to have a weak shock or a strong shock? This actually goes back to your back pressure, right? The pressure after the shock wave. If your pressure difference after the shock wave, or the pressure after the shock wave, is very different or much higher than the pressure before the shock wave, you have to have a very strong oblique shock, right? Because the adjustment necessary I mean, we are gonna need a bigger adjustment, right? And a bigger adjustment means a stronger shock wave or something that's closer to a normal shock wave, right? If your back pressure or pressure at the outlet is not that different, then you are going to have a weak shock, right? For aerodynamic purposes or external flows, this pressure difference is smaller. What does it mean? It essentially means that we are going to have a weak shock, or a shock that is deflected a little more. The shock angle itself is smaller. Okay, it differs more from the normal shock wave. For internal flows, it is a little harder to determine this, because in the internal flows we have a lot of control over the pressure after the shock wave, right? And this is an internal flow. We can close up the pipe. At the end, we can just, right? We can do a lot of things with pressure. We don't really have that liberty with the external flows. So, but usually, strong oblique shocks happen in internal flows. But for your case, you are usually in this class, you are only dealing with weak shock waves. Okay? You will probably given a beta and you will be asked to find a deflection angle, so you don't really have to make a decision, right? Does that make sense? But one question remains. You have a question? Oh, you had a question?
What's an example of internal flow in airs? Is that like ramjets?
Propulsion, yeah. Duct flows.
Duct flow?
Yeah.
Gotcha.
All of the flows in propulsion are internal flows.
So
But that doesn't mean that we are going to have a lot of. That doesn't mean we are going to have a lot of strong shocks in propulsion. It really depends on the situation. Yes.
So having a strong shock, does that mean it's going to have a higher speed, or
After the shock or before the shock?
after the shock?
It's going to have a lower speed, right? Because we have a higher pressure downstream. So we are going to we are going to be forced to have a lower speed, right? The adjustment is going to, I guess, change the flow to adjust to a very high pressure. Okay?
And vice versa in the weak shock wave where we're going to have
Lower pressure. Lower compared to a very high pressure. The pressure is going to be higher than before the shock anyways, right? But lower pressure compared to a strong shock. So this, yes.
Why is a strong shock closer to normal to the flow than the weak shock?
What is the strongest shock wave that we discussed? Normal shock. So a strong shock is going to be closer to normal shock, right? And so, because of the fact that we have a concept called weak shock wave, this essentially means that after an oblique shock, we can still have a supersonic flow. So your fluid velocity is going to decrease, but it doesn't necessarily mean that it is going to be less than 1, right? There are a lot of cases that we are going to have still a supersonic flow, okay? And it really depends on the geometry, depends on the situation, depends on a lot of things, right? But what is the solution procedure when it comes to oblique shock waves? Essentially, you have to determine either beta or delta, right? Based on a given beta or delta or theta, right? And also a given Mach number. And then you find the normal component that's normal to the shock, right? You have to find the normal component, you go to the normal shock table, find the M2, and so on and so forth, right? They definitely are going to solve an exam. So, is there any questions so far?
This is the last one I'll ask. Can you go back to the graph?
This one or the other?
So as Mach number increases, it narrows, right? Or is it the other way around? Sorry.
This is What do you mean as Mach number increases?
So like,
Let's actually go to the original plan.
yeah, that's what.
So this is in the direction of increasing Mach number. So this has a higher Mach number.
So it does.
Difference between the. I mean, I'm not sure what you mean by narrow though.
So it's like, I guess it's like kind of flattening out as you go faster and faster. Like the strong shock is becoming closer to the weak shock in terms of deflection.
There will be a higher range of shock waves because we have a higher Mach number. But a strong shock, I don't know if I can agree with your understanding of this.
So if you look at like Mach number of 2, and then
Two.
you compare it to Mach number of 2.6, and then you just pick like 2 random points on the, I forget what the x-axis is, theta,
Yeah,
and then you compare it to beta, like I guess the
you're gonna get a lower
increase.
beta. Yeah, you're gonna get a lower beta for the same theta, right? Okay. So I have one more question before moving on. Just Nicholas actually reminded me of this unknowingly. No, no. I mean, you are not going to be graded. So, what is going to happen after this nose? Let's say your theta is here. What is going to happen? What does it mean for the shock wave? Why do we have an edge? Why there's a curve? Yes.
This is because are we gonna be like subsonic because
We are always in the supersonic, the upstream shock wave. We are always in the supersonic region.
Does it mean like a shock wave with that theta can't exist at that Mach number?
Exactly. So a shock wave in that theta cannot exist, and with that theta and that Mach number cannot exist. But we need to have the adjustment. That is when you are going to have a detached shock wave. So that bow shocks you mentioned, as usually when we have the, let's say we have this blunt object, this bow shock here is a detached shock. It is detached from the body. So if you exceed this theta, your shock is going to detach from the body, right? That's what it means. So if you had a condition with a theta that exceeds any of these lines, you are going to have a detached shock for that specific geometry, that specific case. Okay. So we understand the shock waves now. Right? We understand the waves that are going to increase the pressure and lower the velocity. Right? Before moving on, just want to know, what do you think the difference would be between a two-dimensional case and a three-dimensional wedge? Let's say this is a slender two-dimensional object, something like this, and this is a three-dimensional canonical shape. What would be the difference between these two? This one we already know. We are going to assume it's two-dimensional. It is going to look like this. We have the shock wave. But what will happen in three-dimensional flow?
Assuming you get like this kind of shell around the cone.
What will happen to the streamlines? The shock waves themselves are going to look similar to the two-dimensional shock wave. And you're right. You're going to get a shock shell around the cannon. But what's going to happen to the streamlines is that the streamlines are not going to be parallel after the shock wave like these ones were, because of the waves that we are going to experience in this other direction that we didn't have before, right? And the canonical shock wave, this analysis is actually much more complicated. I don't even think they do this in the compressible fluid flow course. I mean, hopefully they do. Okay, what time is it? Let's talk about the expansion waves. So far we have talked about waves that compress the flow. The streamlines get closer to each other, right? We are talking about a concave geometry. It is concave, right? I'm using the correct one. I always have trouble. Concave geometry. But what will happen to your flow if you are dealing with a convex geometry? Are we going to have shock waves? Here, your flow is compressing. Can we say the same thing here?
Let's do the opposite.
It is going to be the opposite, right? So your flow is going to expand. What does this mean? When your flow expands, what does it mean? What does this mean for your velocity?
Increase.
Your velocity increases, right? The expansion waves are going to work in the opposite direction of the oblique shock waves or shock waves in general, right? So essentially, and this is the nature's response to an abrupt change, right? So your airfoil is moving through air at a supersonic speed. You're going to have shock waves in front of it. But as your airfoil passes through a location in a space, right, that location has to go back to its original state, right? So your nature, not your nature, our nature has to have a mechanism to revert back to its original state, right? I mean, of course, there will be losses, there will be heating based on all of those things, but in theory, it has to have a way to go back to its original state. And that way is called the expansion waves. And I'm only going to be talking about the top of the airfoil.
Pressure is much greater there.
Pressure is going to increase, yeah. That's the idea.
So when you see those like wave riding vehicles, is this what they're?
What is a wave riding vehicle?
You know, they like ride the shock waves.
Ride the shock. You have to show me an example. Doesn't ring a bell for me. Wave riding vehicle. They ride a shock wave.
I mean,
What does it even mean?
Good question. It's like it uses the shock wave that's happening behind the vehicle to like propel itself forward, or like help, I guess. It's like an efficiency.
Uses the shock wave that's happening behind them. Send me a video of this because I can't even imagine this. I've never seen. Is this something that you guys all know about? Okay, so I'm not alone. That's good. I was like, what is happening?
Dream one day I went to this plane.
No, send me a video, then we will talk about it. Okay. Let's actually see what time is it. I'm worried that we won't get to talk about the exam and solve examples. But then we are moving at a very slow speed. Let's actually talk about the expand. What's that?
We need more time in this class.
We need more time for it. I agree. Or I need to talk a little faster. I already talk at a very fast speed. I don't do any of it. What's that? Don't go faster?
Already having trouble keeping up.
Yeah, no, I know. And I'm sorry about it, but a lot of material that we need to cover. And we just added 2 chapters, so this year. Which means that. Okay, so let's just stop for the theory. Let's just stop here. I don't want to complicate the matter even more. Hopefully you are.
Something on this Wikipedia, but it says it's called Wave Rider, and using shock waves to use supersonic vehicles lift to drag ratio, and using something called compression lift to do it.
I will look them up. I'm not familiar with this type of vehicle. Hall thrusters, I could talk for you talk about them for you for 2 hours, but wave rider, no idea.
What's that electromagnetic?
Yeah, plasma propulsion system. Yes, okay, so let's stop here. Let's actually talk about the exam. Your exam, I was thinking of letting you guys take the exam online, right? What do you think? Is everyone, I remember you didn't like online classes, but you like online exam.
I like online exams.
Okay.
I don't feel stressed with everyone around me feeling like I have to compete.
One question, if it's online, is the difficulty exponentially?
Yeah, that's a good question.
If the difficulty is much harder, then that's a...
The difficulty is not going to, you have a question?
Oh, no.
Oh, just you.
Is it gonna be like, if we did it online, is it gonna be like, one way to scan in?
And you have to, yeah, send the PDF file to me.
Okay, so,
Of course.
just, I don't know, if it was like, a multiple, like right in there.
No, no.
It's not gonna be easy.
How can you?
If you don't mind,
No,
can
it
you open it
doesn't
up,
do that.
because I'd have to go home, like. just
Can we what?
From class, yeah.
From like, could you like open, if you did it online, could you like open it up for, like still have the same hours or whatever, but you know, like maybe start at like 2:20 when the class ends, and you can take it up until like 7, so, because I gotta go home to scan it in.
Yeah. We can do 24 hours, and I give you in
Okay.
that span of 24 hours, you have 2 hours to
Okay.
do the exam.
His online exams are nice.
Well, I just have to go home.
He's not nasty about them.
I was thinking since it is the day before the fall break, you may actually appreciate having an online. I don't really like online exams myself.
Not the biggest fan.
Not the biggest fan, no, but I was thinking it may actually benefit you guys a little more. Do we have any, let me actually answer Igor's question about the hardness of the exam, the toughness, I don't know, how hard the exam is. The exam is not, I've already designed the exam. Exam is not going to be harder, but you won't get any questions from the homework. So exactly all of the homework. It is going to be a similar question, but not with the same exact numbers.
Okay.
Okay?
I feel
But it will be
I feel like that works
like
my muscle a little more.
What's that?
I feel like that works my brain muscle a little more.
That's the idea, yeah.
It's just like the not be something. It's not gonna be like we haven't done a homework problem on.
Yeah.
During the
It
training.
is, your homeworks are hard?
No,
No, we were just talking about the first orbital exam.
Someone war flashbacks.
No, it's
Whenever you emailed us,
Yeah,
like,
hey,
if we could
like-
take it again online, I was like halfway through a hike, and I was like, oh no, I gotta get home.
I was like, I don't
Had
want
to
to
rush
take
down
it
the
again.
mountain to get back.
Yeah, it is not gonna be like the orbital exam. So, I mean, the flight mechanics exam, there was no orbital exam. Orbital exam was fine, right?
Yeah, orbital's fine. It was the flight mechanics.
Yeah, no, it is not gonna be like that. So it is going to be, let me put it this way. If you understand the homeworks, and if you understand the question, I'm put 2 questions that I'm going to solve today, right, for the shockwaves, then you should be able to get an A from the exam, right? Unless you forget something and can't finish the exam, right? The exam, yeah. Since I'm going to change the questions a little bit myself, I have to solve them. So I guess I will make sure that it won't exceed the 2-hour time limit, you guys know. I mean, it should take me less, of course. I don't really expect you to solve the questions with the same speed.
Is it like a question that has multiple parts, or is it just like?
I mean, the
one
question,
Little do you know.
Give one answer.
Orbital was A through L.
All built. Whole alphabet.
No, the thermal questions are going to be a little bit different because, thermal questions may have a couple parts, but to answer the first part, you already have to do you have to solve a lot of things, and as long as you have the enthalpies at each stage, it is going to be plug and chug all the other parts, right?
Yeah.
Right?
Yeah. You actually.
You basically solve it in the first part, and then you just write it down.
Yeah.
Okay.
You actually care about our process and work, right?
Yeah, I do care.
Okay.
What do you mean by that?
Because the only test I've taken this semester so far, the teacher's like, yeah, you either get it wrong or right. I don't care about your work. I'm like, well.
No, I do care about the process, right? But sometimes, like, you give me a very wrong process and you claim
Well,
that
yeah.
you should get a partial credit. That doesn't work, right?
No, it's
Just
sometimes
writing
like-
things down doesn't work.
The problem is like where it's like A through D, and then you don't get the number right in A, but you do the right process for B, C, D, but you get no credit for it.
You will get credit, yeah. That's why shouldn't you? I mean, in real world, if you design something like that, you won't get any credit for it. You will probably get fired, right? In real world. But in an exam,
Yeah.
in real world, you will probably have more than 2 hours to like design a power plant. Right?
2 hours, teammates, you know.
Exactly. Yes.
Can you have a little grocery list of what will be on the exam? Like,
Grocery list.
Yeah, like bullet points of like.
So I'm thinking there will be one question from the Rankine cycle. There will be one question from the gas cycles. And there will be one shockwave problem. That's it.
Can we do the shockwave problem?
We will solve 2. So I will give you I mean, I don't think I have a time for a quiz. But I will solve an example for you.
Quick question. Will it be a full cycle?
What's that? No, not those.
Brayton cycle.
The gas cycles are Brayton cycle. I mean, not Brayton cycle, and probably Otto or diesel cycle, but they are essentially going to operate in the same manner, right? So let's solve this. This is the example 2.3 of. This is not the example. This is the question 2.3 of the problem, book problems. Okay. 2.3. I'm going to write it down right here. We want to calculate the stagnation pressure measured by a pitot tube on an inclined ramp. In a supersonic flow. Of course, it's in a supersonic flow. As shown. Just want to give you the complete description of the problem. So we have this type of ramp, 10 degrees. We have the pitot tube, M1 approaching this is 2, and we are also given the pressure, that's the static pressure, 100 kilopascals. We want to find the stagnation pressure at the pitot tube. Okay. So, first thing you need to do here is to determine the type of shock waves and the number of shock waves you're going to have here. Are we only going to have one shock wave or a couple of shock waves?
Well, we have a strong
Look at the graph.
Which graph? I mean, you have to determine the shock wave first, right?
I think we'd have a strong and weak.
A strong and a weak.
Weak, I believe.
So at one location, you either are going to have a strong shock wave or a weak shock or a normal shock or an expansion wave. You are not going to have 2 shock waves at one location, right? So one oblique shock wave here, right? It is probably a weak shock wave because in this course we are only going to deal with weak shock. Do you want to say something? Yes, yeah. I thought you had. Okay. So what do we have? We have the M and we also have the theta. We can find beta from the table.
Wait, is 10 not the beta?
No, it is theta. Did I say beta? I may have said the other way around.
10 degrees is beta.
Yeah, the inside.
It's theta, yeah.
So,
Oh, so
so
that's
it should be
beta.
corresponding to
But
the
is that not the bottom?
shockwave?
No, that's the airfoil. 10 degrees is the airfoil.
Yes, that's
That's-
beta.
So I'm sensing that I may have said the wrong name here. This is going to be your theta, And this angle, the shock angle, is going to be your beta. Now make sure to you have the correct information.
Oh, is that from chord line to shockwave?
From, yes, this is, yes. I mean, I don't really like calling it chord line. It's just the base of the geometry, right? So if you are dealing with a slender object, this is going to be your chord line, but this is where you measure the angle as well. But this is, as long as it is in the same direction as the streamline, you are not going to use the middle line. So it's the angle between the streamline upstream and your, okay? So let's go to this. We have the deflection angle theta, 10 degrees somewhere here, and then the mark number 2. So we should get a beta angle of 30 something. I have 39 here. So, and since you are doing it online, you can actually, everything is open, so you can actually use Google to find this. Yes.
How did you get 6 for theta?
It is 10. I'm sorry, this is not a very good handwriting. 10 degrees.
And one more thing, will that sheet be provided on the exam, or are we going to have to find it?
It is in the book. What I can do for you, I can upload a PDF copy of all of these tables on Blackboard, right? But it is in all of the books, and since this exam is going to be online, you can actually use online resources to do these calculations as well. Okay?
Is that the same for the thermo?
Yes, I will upload the thermodynamics tables as well. Yeah.
Can you go back to the table and show one more time how you find the angle?
Sure. So you are given the theta or delta. There are two different types of, which is 10 degrees. So somewhere here, right? Then you want to find the line with mark 2. This is the mark 2 line. Do you see this? You can't see it? This is, let me actually, the screen, right? Okay. What is going on? Let me go back to this.
If you open it in folders, you can actually write it on.
It should be, yeah, here. So this is going to be mark 2. This line. And then we have the 10 degrees here, right? This is going to be your beta. Okay? Maybe.
So what is the sonic limit in the legend? Like obviously it's a weak shock, strong shock.
Is M2 equals to 1, right?
Also that's like a trend line?
This is the line in the middle. Let's just don't complicate the matter. It is going to be, I don't want to, you are not going to use that. That sonic limit, that is the limit between the weak and a strong shock right there. And this is the line in the middle. I didn't want to explain this one. This is the line in the middle. See this line? This is where the weak shock becomes a strong shock. Right? And at that specific location, your M2 is going to be equal 1. So you're essentially going to supersonic downstream to subsonic, from weak shock to a strong shock. Okay, so we have beta equals to 39. What is the next step here? Find the MN1. That's the normal Mach number. How do you find this? M1 sine of beta. So you plug in the value. Sine of 39 degrees is whatever. You can find it, use a calculator for it. And M1 is 2. I have the final value for myself here is 1.6. So after this weak shock wave, we are still going to have a supersonic flow. Okay? Is this true? Is what I said true?
Yeah.
So based on this number, I concluded that after the shock wave, we are still going to have supersonic flow. Think about it. This is the normal component of upstream Mach number. We don't really have any information about the downstream yet. You have to go to the tables. Okay? So let's go to the tables. How do we use the tables? These tables here. Done. Appendices. For the normal shock wave. So if your M1 is, what was the M1? 1.26, right?
Yep.
Yes. This is the M1, this line. Do you see my pointer here?
Yes.
I mean, you see the line. It's your M2 is going to be 0.8. Does this mean we have subsonic flow after this oblique shock wave? Still no. Because this M2 is the normal, this is M2MN2 from the tables. This is the normal component of the shock wave downstream, right? Which was, what was the number? 0.8. 0.871. I have 0.871 here. Okay. So how can we find M2, the actual downstream Mach number?
You take that one, you divide by sine beta minus theta.
Beta minus theta, exactly. So sine of 29 degrees, right? And sine of 29 degrees is less than 1. So we'll probably are going to have a bigger Mach number. We can't really conclude that the flow is supersonic or subsonic until we have calculated the Mach number. So the Mach number, based on the value I have here, is going to be 1.665. So the flow after this oblique shock wave is going to be supersonic. We already knew that because it's a weak shock, right? But none of the numbers other than this number would have given us that clue, right? And we can also, the Mach number is not the only thing we can read from this table. We can also read the temperature ratio, pressure ratio, density ratio, the total pressure ratio, all of these other ratios we can read from the table, right? These are going to be the same, right? Okay, and the pressure ratio is going to be that all of these pressure ratios are the things that we are really interested in. We want to find the stagnation pressure at the pitot tube, right? Okay, so we have to get the pressure ratios just to make sure that we can, like we have the P1, then we want to calculate the stagnation pressure at the pitot tube. So which pressure ratio do I have to read here to find the stagnation pressure at the pitot tube?
PT2 or P1?
PT2 over P1. So what Igor is telling us is that PT2 is actually going to be the stagnation pressure at the pitot tube, right? Is this correct? The stagnation pressure is the PT, right? So essentially, what Igor is saying is that after this shock wave, the stagnation pressure is going to be the stagnation pressure of the pitot tube, right? Is this correct? No. Why not?
Is the pitot tube ahead of the shock wave?
Pitot tube is not ahead of the shock wave, but we are still in the supersonic flow here. And pitot tube is an object in front of, is an obstacle in front of a supersonic flow. So we have a second shock wave here, exactly. And that second shock wave is actually going to be a bow shock. Okay, what should we do now?
Everything looks okay.
we don't really need to do everything. Once again, this bow shock can be treated as a normal shock by itself, so we don't really need to include the angles and the normal components and everything. We just take this 1.66, right? Take it to the normal shock table and treat this as M1, right? 1.66, right? That was the value. This one. And then we read the pressure ratio for that one as well. We have the pressure ratio for the previous case. So for the previous case, we can actually read P2 divided by P1. For this one, we can find the PT2 divided by P1. This time it's going to be PT3 divided by P2, right? Does this make sense? So this region, we are going to call region 1, region 2, region 3. We are going to read the P2 divided by P1 from the table for the downstream of the oblique shock wave, which based on what I have here is 1.6855. Then for the bow shock, we are going to read the PT3 divided by P2, which from what we have here From what we have here, 1.66, right, is going to be 4.05. 4.05. Yes, 4.05. And PT3 is going to be equal to PT3 divided by P2 multiplied by P2 divided by P1 multiplied by P1, right? We have this ratio, we are given this number. You can just plug it in here, and you will eventually find 683 kilopascals. Okay?
Wait, PT3 is that, or is it just P3?
P3, that's the stagnation pressure at the pitot tube, right? So we are looking for the total pressure or stagnation pressure, right? Do we have any questions about this?
So, what direction is that Mach 2 flow in? Like, I'm getting confused with like what's the normal direction, what's the X, Y.
Okay, this normal direction, this is going to have two components. Let's say this is, it should be 39 degrees, so the shock is like this, right? We are going to have one normal component like this and one tangential component. This is going to be M1N. Then we're going to have M2N.
Okay.
Okay.
So the M2 is flowing directly out the pitot tube.
Yes.
Okay.
Well, that doesn't have anything to do with the direction of the shock.
Well, but that's just where I was getting confused. Is like why we can use M2 for the pitot tube.
No, because there is going to, okay. M2 is still supersonic, right? And there is an obstacle in front of a supersonic flow. So you will see a shock generation, shock formation.
No, that makes sense now.
Okay.
That's just which direction it was in.
Yeah, it is it's moving in this direction. Is this, but yes.
How do we know we're able to treat that second shockwave as a normal?
Okay, so we can actually, whenever you have an object in front of an upcoming flow, an object like this, not an object that can be like tangential to the flow, right? This flow can move around, right? Or an airflow, but this is going to stop the flow in its track, right here, right here. This is a huge obstacle. So you're gonna have a detached bow shock, right? So if it was like this, if instead of this pitot tube, if our geometry was like this, then we would have had another oblique shock wave, right? Does this make sense?
Yeah, and we can only assume it's normal since we're measuring right at that tip. If we were measuring like somewhere a little back, we would have to find a number
oblique or something like that.
Can you repeat your question?
We can only treat it as normal, right? But as that, like since we're measuring
Right in front of the pitot tube.
Yeah.
But if you are moving a little further from the pitot tube, you haven't arrived at the shock wave yet. So your velocity is going to be your M2 still.
Right.
Okay? Yeah, is this, that's it?
I think
Sorry.
Go ahead.
I was wondering if pitot tubes are actually pointed like that.
They are
On
pointed like this.
supersonic.
Yeah,
It's like, it's.
they are pointed like this, yeah. And there will be, they are
It's
pointed like
like normal to the,
They have to be, yeah.
or the second straight line, I guess.
Yeah, it has to be normal, yeah. Okay, so we are out of time. I wanted to solve another example, but we are out of time. Hopefully you won't have any.
What's the example number that we didn't get this one?
This